In this video, I'm going to be explaining an important evaluation measure that we use in all contrastive learning, namely uniformity and alignment. So they explained this evaluation measure in this paper in 2020, Understanding Contrastive Representation Learning through Alignment and Uniformity on the Hypersphere. Contrastive representation learning has been outstanding successful, and we identified two key properties related to the contrastive laws. One of them is alignment, which is closeness of features from positive pairs. They want them to be very close to each other. And the second one is uniformity. We want the uniformity of the induced distribution of normalized feature on the hypersphere. And we proved that asymptotically, the contrastive loss optimizes these properties and analyze their positive effects on downstream tasks. Especially, we introduce an optimizable metric to quantify each property. Extensive experiments on standard vision and language confirm that a strong agreement between both metrics and downstream task performance. Directly optimizing for these two metrics leads to representations with comparable or better performance at downstream task than contrastive learning. This is an alignment, so when we have an image, we can create augmentation. So assume that X is one of them, Y is the other one. And you see because there are positive pairs, we expect them to have very close distance. So in the hypersphere, this is the concept of alignment. We want to be aligned with each other as much as possible. And this is the uniformity. We don't want to collapse at just one particular area or dimensional collapse or just one point. We want to be distributed along all spaces in our region. Because if we do that, then we can do classifier easier, and there is no collapse to a particular, because if it is collapsed to a particular region, then we cannot separate it. It's hard to separate it, and noise is involved, so it's not even robust. So that's why you see that your training loss is decreasing, but suddenly you cannot improve. For example, you cannot improve the accuracy more than 59%. And that is because in your prior steps in your pipeline, there is some point that something has collapsed, either a collapse to a subspace, or even worse, collapse to just a single point. And these are the contributions that the quantify metrics for alignment and uniformity as two measures of representation quality, and it proved that the contrastive loss optimizes for alignment and uniformity asymptotically, because there is a trade-off. Both of them, we want both of them to be fine, and empirically we find strong agreement between both metrics and downstream task performance. But despite being simple in form, our proposed metrics, when directly optimized with no other loss, empirically lead to comparable or better performance at downstream task than contrastive learning. The popular unsupervised contrastive representation, because contrastive learning was originally started by unsupervised, or we call it self-supervised learning, but then people in Google use it for supervised learning as well, and of course semi-supervised learning. And here it assumes a way to sample positive pairs representing similar samples that should have similar representations. And P data is just the data distribution, and P of pos is just distribution of positive pairs. And the only assumption that we have is that distribution should satisfy, it should be symmetric, and it should be matching marginal. Then we consider the following specific and widely popular form of contrastive loss for training an encoder. So we go from Rn to the hypersphere, and this loss has been shown effectively by many recent representation methods. So F is here is in hypersphere. It's not just simple the classical approach, but we are working on the hypersphere. And tau theory is the temperature hyperparameter, but there is a necessity of normalization because without the norm constraint, the softmax can be arbitrarily sharp by simply scaling all the features. And Wang provided an analysis on this effect and argued that the necessity of normalization when using feature vector dot products in cross-entropy loss. And many empirical works are motivated by InfoMax principle of maximizing the mutual information between f of x and f of y. And usually they interpret this contrastive loss as a lower bound of that mutual information, which has a nice theoretical justification. The contrastive loss encourages learned feature representation for positive pairs to be similar while pushing features from the randomly sampled negative pairs apart. So the loss should prefer to these alignment and uniformity. When we say alignment, it means that we have two samples forming a positive pair, and they should be mapped to nearby features and thus be mostly invariant to unneeded noise factors. The other evaluation measure is uniformity, that feature vectors should be roughly uniformly distributed on the hypersphere, preserving as much information of data as possible. And to empirically verify this, we visualize CFAR10 obtained using random initialization, supervised predictive learning, and unsupervised contrastive learning. You see how these two measures, alignment and uniformity, for both supervised predictive learning and unsupervised contrastive learning. So you can write the contrastive loss as expectation of this dot product between the representations of the two augmentations, as well as this sampling expectation over positive sample distribution and data distributions. So because this term is always positive and bounded below, the loss is smaller and having more aligned positive pair features. Suppose the encoder is perfectly aligned, it means that probability of f of x is equal, of course x and y should be positive, then minimizing the loss is equivalent to this expectation, which is just maximizing pairwise distances with log sum exponential transformation. And intuitively, pushing all features away from each other should indeed cause them to be roughly uniformly distributed. Because if you push them away, then intuitively we expect that they go and become like a uniform distribution. So we need a way to measure alignment and uniformity. We have this metric for the alignment loss is defined with the expected distance between positive pairs. X and Y are positive pairs, and this is the positive pair distribution. So X and Y are just your augmentation of an image. Of an image can be augmentation which has X and Y, or even in NLP we have augmentations, for example one sentence and the other sentence, that they have dropping mask. We use drop masking in order to create these augmentations. It's not as simple as computer vision, but even in the NLP we can do these augmentations. We want to use the uniformity metric to be both asymptotically correct and empirically reasonable with finite number of points. To this end, we consider the Gaussian potential kernel and define the uniformity loss as the logarithm of the average pairwise Gaussian potential, because this G is just the Gaussian potential kernel. So the set of Borel probability measures is the unique solution of this minimization. And these Borel measures, weak convergence, all of them are in abstract mathematics, in measure theory, which is a branch of functional analysis. For example, for each n, if f x n endpoint minimizer of the average pairwise potential, the normalized counting measures associated with the sequence converges weakly or weak star to sigma d. Designing an objective minimized by the uniform distribution is in fact non-trivial. For instance, average pairwise dot products or Euclidean distances is simply optimized by any distribution that has zero mean. Among kernels that achieve uniformity at optima, the Gaussian kernel is special in that it is closely related to the universally optimal point configurations, and can also be used to represent a general class of other kernels, including Rees S potential that I've explained in a different video about Rees potentials. We say an encoder is perfectly aligned if f of x is equal to f of y. Of course, x and y should be positive pairs, should be positive augmentation of an image, x and y. And we say an encoder is perfectly uniform if the distribution of f of x is the uniform distribution on the hypersphere. Now the realizability, because it has a limiting behavior, this contrastive learning. So we note that it is not always possible to achieve perfect uniformity. For example, when the data manifold in Rn is lower dimensional than the feature space. Moreover, in the case that probability of data, these distributions are formed from sampling augmented samples from a finite dataset, there cannot be an encoder that is both perfectly aligned and perfectly uniform, because perfect alignment implies that all augmentations from a single element have the same feature vector. Because if you are perfectly aligning everything, then it cannot be uniform. Then you miss uniformity. So they have a theorem that says for if a fixed tau as the number of negative samples, the contrastive loss converges to this limit. This is the limit of contrastive loss. And the first term is minimized if and if f is perfectly aligned. So if it is perfectly aligned, and the second term, if perfectly uniformly encoded exists, they form the exact minimizer of the second term. And for the convergence in this equation, the absolute deviation from the limit decays in order of this. And we have relation with feature distribution entropy estimation, because when P of data is uniform over finite samples, the second term can be alternatively viewed as a resubstitution entropy estimator of F. And X follows the distribution that generates X sub I, yi Mises Fisher kernel density estimation. And P hat is just the KDE on samples using this kernel. And it has relation with the Infomax, because many empirical works are motivated by Infomax, maximizing the mutual information between f of x and f of y when x and y are just positive augmentations. However, the interpretation of contrastive loss as lower bound of mutual information is known to be inconsistent with its actual behavior in practice. So our results instead analyze the properties of contrastive loss itself. And by considering this identity, we can see that while uniformity favors large entropy, alignment is stronger than merely desiring small entropy. So we empirically verify the hypothesis that alignment and uniformity are desired properties for presentations, and we have these two metrics, alignment and uniformity. We conduct extensive experiments with these CNN and RNN on these four popular benchmarks. And for example, this is the PyTorch implementation of alignment. And we take the normalization power to alpha and take the mean, or the uniformity, we just use the P distribution of PyTorch and then power to 2, and then we take the expectation mean and then the log of that. So these are the metrics and performance of ImageNet 100. So each point represents a trained encoder with its x and y coordinates, showing loss of alignment, loss of uniformity metrics.